us about his recent work jointly with Arai, Weiner, and Weiermann on Gutstein principles of intermediate strength. Please, David, welcome. Begin.
Well, thank you, and thank you for the invitation. So this talk is part of a wider project about Gutstein principles, and my co-authors, Professors Arai, Weiner, and Weiermann, have been working on this for a few years, and I'm very lucky to be now included in this project. So I'd like to begin by remembering what the Gutstein principle is, the original one that's from back in the day. So the idea is that we're going to define a sequence of natural numbers, and they're a little bit contingent on a notation. So you take a number m, so in our example, let's say that m is 22, and you write it down in base 2 in binary, basically. And but the rule is that the exponents are also written in binary. So you end up with these towers of 2. And the way we define a sequence is that once I have this written in binary, I'm going to replace every 2 for a 3, and then subtract 1, right? So this number is something that looks like it's a lot bigger, but we take a little tiny bit off at the end. And then we continue in this fashion. So now we have this new number, and we replace every 3 by a 4 instead, and we subtract 1. And again, we're getting numbers that are very, very big, and then subtracting just a little bit at the end. And so the big theorem is that this will eventually turn being 0, which is something that should be very surprising when you look at the way this is increasing. But it's a little bit less surprising if you think of these as ordinals. So if you think of the structure, this in each 2, just forget that it's a 2. It's just a placeholder, and it looks a lot like a Cantor normal form, right? If we continue this way, the next term in the series, it's still an ordinal. It's a little bit smaller because its last part decreased, and then it gets even smaller. So we know that every decreasing sequence of ordinals will eventually reach 0, and that's how we get this result. Now, let's break it down a little bit. So what do we need to define a Gutstein process? There's some creativity here, so we could define maybe a variation. So first of all, we need a notation system for natural numbers. In this case, we're using the exponential. Then we need a notion of normal form. So every natural number is written in some specific way using the exponential, in this case in hereditary base k. And then a notion of base change, which is once I have something written in base 2, I need to be able to lift the base to 3 to get my new numbers. And then with this, I could define the same recursion that I showed you before. So in this case, we want to talk about a version that uses not the exponential, but the Ackermann function. So let's just agree on the version of the Ackermann function we're going to use. I like to define this value on -1 to be 1, just to make the definition a little more uniform. So you think of this as a family of functions indexed by a, and I'm going to omit the k, but this k is important. I omit it because we think of it as a fixed parameter for now. So a naught is just the exponential function with base k. And then to evaluate in a successor, what I do is I take the previous branch, I apply k times, and then I take the same branch that I'm defining now, and I apply it to the smaller value, to a previous value of b. So if you just look at this, it might not be so obvious that it's well defined, but you could check it by an induction on a with a secondary induction on b. And then, well, these are functions that grow very quickly, but they are always defined. So we're going to use this for a notation system. The idea is we have a 0, we have a Riemann function, and we use this to write down natural numbers. So again, when we have the exponential notation, we had a canonical way to write things down. So now, well, it's not so clear. Is there a single canonical way to write it down? Write down a number using this notation? One, but there's some reason. Our goal here is to take a number and write it in this way. The idea will be that once I've written this down, then I could write b and c also using the Ackermann function in a hereditary way. So think of this as a main term. And so how do we do this? Well, the Ackermann function is a hierarchy of functions indexed by A. And we want to use the biggest possible branch because that's just the one that grows faster, the one that has most strength. So we're going to choose a maximal possible value of A weak because as long as A little a of naught is less or equal than M, then I could choose a suitable B. And so this is my internet connection is unstable, or is it fine?
Yeah, it's fine. It's
Okay.
slightly, there is a slight disturbance, but it's not that big for me. Mm-hmm.
Okay, let me know if something's not, doesn't sound right. So once we picked our value of A, then we could choose B, which will of course be the biggest possible value that we can given this fixed A, and C will just be the remainder. And I'm going to call this a simple Ackermannian representation for M. Now this by itself is only the, let's say, the beginning of a normal form, because we still have to represent the parameters in some way. And there's so the term that I assign to M is going to be denoted NFK of M. So the normal form, the K normal form of M. And there's actually going to be two attitudes that we could take. So as I told you, the parameter A gives you the branch of the Ackermann function. So one idea is to just say, well, this is not really a number we're writing down. This is just a function we're using. So it's only B and C that should be written down in normal form. The other attitude we could take is to say, no, A is also part of the notation, and A should also be written down using the Ackermann. So as an example, you take 6, you evaluate A1 of 0, you will see it's 4. And you cannot fit any bigger branch in there, so 6 will be written like this. With respect to option 1, we need to develop the 2. We need to develop the 0 is already a constant, right, in terms of option 1. Option 2 says, no, we should also write this index down using Ackermann notation. So that's what the hereditary notion looks. Now, each one of these comes with its own notion of base change. For the unary version, when you do it's the K is the base. When I change base from K to L, I replace every K by an L. And I do so inductively in B and inductively in C. But like I said, A is treated just as a number. It's just a parameter, it's fixed, we don't move it. With the other attitude, A also gets the same treatment, right? And the reason that I stress that we have these options is that each one will give us a different Goodstein process, and they will actually behave quite a bit different. So how do we define our Goodstein sequences? They're the same as with the exponential, but using this new notions of base change. So we want to define a sequence that it's a Goodstein sequence for M, and it's indexed by I. And this alpha could be finite or infinite. We'll see that it's finite, but in principle, we're open to it being infinite. So you start with some number M, whatever you want. You write it M in base 2, and then you raise it to base 3 and subtract 1. And then you do this recursively. So then in the next stage, when I is 1, you write the number in base 3, raise it to 4, subtract 1, and so on and so forth. And we terminate whenever the sequence reaches a 0. If not, we just go on forever, either way. So let's give some examples to simplify notation. Big A is going to be the the base 2 Ackermann function. Big B is going to be the base 3 Ackermann function. So let's start a sequence for 6, and we're in unary now, right? So remember, the A is just a parameter. So we write this down in its normal form. We raise the base to 3. And now I'm just going to expand this a little bit. So what does B1 of 0 mean? It means that you apply the previous branch, so B0 in this case, K many times. K is 3 here. And because I'm at 0, you just apply it to 1. And now we remember that B0 is the K to the B, so to the little b. So then this becomes a 3 to the 3 to the 3 to the 1. This is a 3 to the 3 to 0. And well, you evaluate it, comes out to this. There's no point in writing this down but you could tell that we got a much, much bigger number than we started with. From 6, we went to 3 to the 27. So what's the difference between the two? In this example, I'm not going to try to write down the numbers. They're big numbers if you try to write them down in exponential notation, but it's some number. So we start a sequence here. And with unary sequences, this is the way the number looks. We raise the base. Now it's we have b2 of 0 minus 1. And you can imagine, for example, when we went from A1 to B1, things blew up. You can imagine that this, and the second branch is going to blow up even more. This is not even worth trying to explain what it is. With the hereditary attitude, we also write down the 2 in Ackermannian notation.
Mm-hmm.
And so when we change the base, we also have to change the base here, which gives us, now, not only are we passing from the A to B, not only are we changing base, we're also changing branch. So, I mean, if this is something I didn't want to spell out, then, you know, here, don't even try. So these things, these already grow very quickly, and these grow extremely quick. And so what do we want to know in this talk? There's 2 questions. Are these finite? And I mean, you could probably guess the answer, but that's a question for now. And what is the proof theoretic strength of this assertion that they're finite?
Mm-hmm.
And so for the proof theoretic, I'm going to stick to second order arithmetic just as a benchmark. So remember that second order arithmetic, you take a piano and you add set variables, and you get to quantify over all subsets of natural numbers. So the second order version of piano arithmetic is ACA naught. The idea is, well, this is one way to explain it. You have the induction axiom that says that every non-empty set has a least element, and you add an axiom that says that if I have a set X, then I could build its Turing jump, and that's also a set. ACA naught prime, well, if you think about it, if I take a set X, then with this axiom, I could build its Turing jump, and I could build its Turing jump, and so forth. But ACA naught doesn't know that you could do this indefinitely. It just knows that you could do it for every single concrete standard number. ACA naught prime quantifies this internally. It tells you that you could build for every natural number the Turing jump up to n. So now this n is internally quantified. But you cannot build the omega jump. Each one of these is a separate set. So if you want to put them all together into a single omega jump, then you get a stronger theory that's ACA naught plus. And all of these theories live below ATR naught. So ATR naught stands for arithmetical transfinite recursion. The zeros are because we use induction axiom and not the full induction scheme, which is stronger. And now we say, well, then I could iterate that ordinal alpha. So this is quite a strong theory. And how do we measure their proof theoretic strength? Well, we use ordinals, in this case, below gamma naught. So let's talk about gamma naught a little bit. We're in a hierarchy of functions on the ordinals now. Sorry? So the first function is the base omega exponential. And when I have a alpha greater than 0, I start to enumerate all those things that are fixed points of the previous functions, common fixed points. So in this talk, we mostly are going to work with the epsilon and the omega exponential. So epsilon alpha is phi 1 alpha. So these are the numbers that are fixed under psi goes to the omega to the psi. And again, mostly we're going to work with these 2 functions. But in general, we have a way to represent ordinals using these operations. So every ordinal that's not 0 can be written uniquely as phi alpha beta plus gamma. To make it unique, you have to make the gamma be less than the original ordinal, and you have to make beta not be a fixed point of phi alpha, right? So if you have these 2 rules, then you have a unique notation. And gamma 0 is now the first fixed point, but with respect to this other argument. So that's going to be bigger than for example, these things. All right, so why is gamma 0 relevant with respect to these notation systems? Well, in part because as long as I'm below gamma naught, I can ensure that these three parameters are all less than the ordinal I'm writing down, so I could apply induction or recursion to them. And in particular, we're going to use this for fundamental sequences. Now, I need to talk about these before I prove theoretic strength, because we're going to use these to define proof theoretic strength in this context. So it doesn't matter so much that this is a big definition. It's a lot of cases. It doesn't matter so much that you read through it in detail. But the point is that we're defining sequences such that for every ordinal, for every limit ordinal, as n goes to infinity, this converges to the limit. So let's look at some examples. Remember that this was the omega exponential. So omega to the beta plus 1 is the limit of omega to the beta times 1 times 2 times 3 and so forth. That's the standard definition, actually. So that's what you see here on the right hand side. And these five functions are all continuous. So here, for example, to reach a limit, I just have to approximate the argument, and then I know that by continuity I will converge to the value of phi alpha lambda. Now, number 5, I don't want to talk about it too much right now, but I want you to look at it a little bit and remember the shape of it, because I will discuss it a little bit more later. So whenever alpha is a successor, then this thing on top is just x. So you take the x-fold iteration of the predecessor of alpha applied to the same phi alpha branch, but to the predecessor of beta. So of beta plus 1. So that's going to pop up a little bit later. Now, we're going to use this to define. Sorry?
So this choice of fundamental sequences is somewhat deviating from the standard one, right? So from the textbook, or is it more or less the same?
It's more or less standard. I put a 1 here. You might see a 0 sometimes.
Mm-hmm.
That's just so that you don't start at 0. But yeah, it's pretty standard.
Mm-hmm.
All right, so we're going to use this to define proof theoretic strength. So in particular, we're concerned with the pi 0 2 ordinal. So you define this to be iterated fundamental sequences. If you notice, as n increases, this decreases because I start xi, then xi of 1 is smaller than xi of 1 of 2 is smaller than that, and so forth. And so we know that gamma 0 is an ordinal. There's no decrease in sequences, so this has to stop at some point. However, this is hard to prove. So when do we say that T has proof theoretic strength lambda? Lambda is an ordinal. Well, T should not be able to prove that the stepping down the fundamental sequences below lambda always terminates. But if you bound it uniformly by some alpha, so you say, well, I'm only going to stop at this alpha that's strictly below lambda, then T should be able to prove that these instances do terminate, right? So that then lambda is the boundary of what you can prove in terms of this type of termination.
Mm-hmm.
So these are just facts. ACA naught has proof theoretic strength epsilon naught, which is 5, 1, 0 in the Veblen notation. ACA naught prime has proof theoretic strength epsilon omega. That's a bit larger. It's not the first epsilon number, but you just go up an infinite chain of epsilon numbers. ACA naught plus, it's a little bit bigger. Now it's the first fixed point of the epsilon function. So this ordinal satisfies alpha equal epsilon alpha. And finally, ATR naught has proof theoretic strength gamma naught. So we'll use these facts. And now this is a little bit of a general slide. It's in general, how do we prove that a Goodstein process terminates, and also that it's independent from some given theory. So we're going to define these order types. This, think of it as a base. This is the value, and they go into some ordinal lambda. It should be well picked from the beginning. So as I go throughout my Goodstein sequences, remember M is G0 of M, the first element of the Goodstein sequence. that's G1 is the second element, and so forth, I should get a decreasing sequence of ordinals. Notice that the base is changing, and that's because the base has to do with the base in which I wrote down this number. So M I write in base 2, G1 of M I write in base 3, and so forth. So we want to have the appropriate base here, right? And then we want it to decrease, but not too quickly. So we don't want it to decrease more quickly than the fundamental sequences. So if I take one of these numbers and I apply fundamental sequence to it, I don't want to get something bigger than the next element. Item 1, I already have termination because, again, this is a decreasing sequence of ordinals. With item 2, item 2 will tell us that this is no faster than stepping down the fundamental sequence. So basically, if the Gaussian process terminates and this bounds the dropping down the fundamental sequence, and therefore it will give me a proof that the other process terminates, which I already don't have if lambda is a proof theoretic ordinal of T. Now, just a note, I'm not going to talk about this too much, but this requires that the fundamental sequence have the Bachmann property. If not, this is not quite enough for independence. But these are nice. Wait, I did something. I think I pushed the wrong button. Give me a second. Okay, here you go. All right, so now, how are we going to define this function O? Well, it's very tempting to do this. Look at, this is the Ackermannian normal form. This is the Veblen normal form. They look suspiciously similar, I would say. This is the Ackermannian recursion. And from the fundamental sequences that I use a little bit, rank 8 times, I apply the same branch to the predecessor. So it's really tempting to say that the order type is going to be basically replace the Ackermann function by the phi function and apply this recursively to the subterms. So that would actually end up working if we just want termination, but we could get away with much less. And to do this, we note that if we're below phi 2 of naught, then the omega exponential and the epsilon function are all we need to write down ordinals, right? So we're in unary subscripts now. Remember that means that A is just it's a parameter. It's not really part of the notation in some sense. So I'm not going to move it. And the base change operation is not applied to A. Here A is just A. So we define these order types. This prime is because of ACA not prime. It has to do with that theory. That's why it's there. So every natural number goes to epsilon omega, to something below epsilon omega. 0 will always go to 0. That's general rule. And if I have a notation that like this was going to happen, this Ackermannian term is going to go into an omega exponential, with the A being the index of an epsilon function, and the B, well, we treat it as an ordinal and just add it here, right? So this is going to be the order type that we assign to this notation. And that's going to be enough. So just a reminder, the definition of the Gaussian sequence is you have your notion of base change, in this case, a unary one. You start at some number. At the next stage, you take the number, you write it in base I plus 2. Every I plus 2 becomes an I plus 3, subtract 1, right? That's our sequence. So the theorem is that this sequence with the unary subscripts and its associated base change operator always terminates, but that this is independent of ACA not prime. So the way you prove this is basically to show that the mapping that I defined satisfies these required properties. And I'm going to go a little more detail on what the proof looks like. I'm just going to mention the key lemmas. So first of all, this operation is, the base change operation is increasing. If I take a smaller number, then it's base change, and I apply base change, I get a smaller value. That's going to be useful. Sorry?
Yeah, all right, yes.
Okay. that's going to be useful to show that when I take a number and I change base, I replace k by l everywhere, I end up getting something that's also in normal form. So why would I care about monotonicity here? Well, I need to have these maximality conditions on the B. So if the base change scrambles things around, then it's going to be trouble, right? So we want to make sure that if I compare some values of B, then the comparison still holds up after the base change. All right, so then, okay, so apparently this button goes all the way to the end. Let me go back here. Yes, we're here. All right, so this is essentially the same property as base change, except that now it's order types. These are also monotone under inputs. And finally, if I take a number and I apply a base change to it, the order type of the number with respect to base k is the same as the order type of the new number with respect to the new base. And this comes directly from the preservation of normal forms, because it just has the same shape, the ordinal before and after base change, and the number, sorry, before and after base change, and the ordinal that I assign to it, I assign to it with in terms of the shape that its notation has. So if the normal from here and here are the same, then the order types should also be the same. All right, so these lemmas are not easy to prove. The proofs are elementary, but they're a bit messy, many cases, you know. But once I have this, then it's easy to see whether the sequences are finite. So I look at so suppose that gk of m is positive. I look at the next term, but I look at its order type. This is just a definition of the Goodstein sequence. Then because the order type function is monotone, this is less than if I had not subtracted a 1. But because the base change preserves the order type, this is the same as if I took the order type with respect to k plus 2, but having never done the base change. And that's so this element is the order type that I assign to the next in the sequence, and that's to the previous. So when k is 0, I have that O prime of 2 of m. This is greater than this. And then when k is 1, it's greater than this, and so forth, right? So this a decreasing sequence of ordinals and must be finite. All right, so for ACA not plus, I'm going to go into less detail. It's almost the same idea. So remember that now the index A is also treated as being in a certain base, and it's also we also apply the base change to it. So now we get a function into a bigger ordinal, phi 2 of naught. And the difference here now is that the A is treated as an ordinal as well. So now it's not going to be epsilon n for some natural number n. It really could be epsilon of any ordinal, you know, as long as I'm below this. So the theorem is now that these sequences are also terminating when I have hereditary subscripts, but now it's independent from ACA not plus.
Mm-hmm.
And the proof is the same. But this leaves a question. I showed you before that the Ackermann function looks a lot like the Veblen function, and we seem to lose a lot of strength. So what happened here? Well, the reason is that we're actually not using all of the Jews that we have from the Ackermann function as a tool for writing down natural numbers. So what we're going to do is try to get more information with these functions. And this is called the sandwiching procedure. It starts the same as before. You choose an A1, which is the maximal branch of the Ackermann function that could fit below M. And then I choose a maximal B1 that I could apply little a1 to. Mm-hmm. But then we don't stop here, because what could happen? Maybe this is really small. Maybe it's much smaller than M, and so much smaller that it could still fit more branches of the Ackermann function in there. So then I take the maximal next value that I could apply, and I apply it to my previous approximation, and then I raise from M1 to a bigger B2. So this at first sight might look like the little a1 is lost, but the idea is that it's always going to live inside the B2, so it's still going to be there somewhere. And we continue like this until we can continue no more, meaning that we have the nth approximation where even the smallest branch of the Ackermann function is already going to give me a value that's too big, and then we stop. So let's write 16 in base 2 without sandwiching. I'm going to do some computations to see how this works. So first of all, I claim that this thing is smaller than 16. So remember, we're in base 2, so I apply the previous branch twice. 0 becomes 1. And this is 2 to the x, so it's 2 to the 2 to the 1, which is 4 less than 16, right? All right, so I also need this computation here. I claim that this is bigger than 16. So that's, I apply the previous branch twice, and then I apply the same branch to the previous value. That's the rule, right? And then I elaborate on this. That's going to be, well, we have it here, that's 4. So that gives me 2 to the 2 to the 4, which is bigger than 16. And the final computation I need is this thing. This is a big number. I don't want to know what it is. Let's just estimate it. So this is, again, 0 becomes a 1, and you apply the previous branch twice. And this, of course, is going to be bigger than a1 of 1 because I'm applying a1 once again. And we already know that's too big. All right. So from these two inequalities, the first and the third, we know that the first branch, so the branch that we're going to use, the maximal branch is 1. And from the first and the second, we know that the maximal B is 0. So that's the Ackermann term that we use. And the remainder, you see, it's pretty big. It's almost the whole thing. So in normal form without sandwiching, we end up getting this sum. Or you could write a1 0 times 4. Multiplication is not officially part of our notation system, so I leave it like this. With sandwiching, what happens? Well, it starts the same. So a1 is 1, b1 is 0. This analysis still applies. But then we know that 16 is 2 to the 4. So we could still apply a naught to it. So that's what we do. And the normal form is, so now a2 is 0, b2 is 4, because we could still apply a 0, but we cannot increase this value anymore. And because I cannot stick more branches in there, that's it. That's the normal form of 16. And this gives me the full strength of ATR naught. So when we're using the sandwiching normal forms, we always treat A, B, and C, all of them, as being written in the same form, right? So the base changes apply to the three inputs. And the order type that we're going to use now is the one that we thought seemed reasonable back then, which is that the Ackermann function becomes the Veblen function. Now this is just a technical detail. This is going to be the fixed point free version, but it's roughly the same spirit. And right, so the theorem here is that this process is also terminating, but now we get independence from ATR naught. So what do we conclude? Well, we can use this notation to write down very large numbers. So if you really are concerned with talking about big numbers in mathematics, maybe you could forget about exponential notation that we use all the time and use a systematic Ackermann notation. If you do it with some nice criteria, then you could make it so that numbers are canonically written, and you could just look at two numbers, and just by seeing that they look different, knowing that they're different because they were chosen canonically, like we do with base 10 or base 2 or whatever. We can use these notation systems to define Goodstein processes. These are much slower than the original Goodstein version. It takes much more time. Well, they're faster growing, which means that they take more time to become 0. And actually, the precise way that we use the notation, the way we set up these normal forms, makes the proof theoretic strength vary wildly. So here's, I hope I didn't ruin anybody's question with this. So, well, what if we're even more clever and we use the Ackermann notation to come up with principles of higher proof theoretic strength? And actually, that's impossible. So in recent work, we've shown that that the sandwiching procedure gives the absolute longest good thing sequences you could get from this system of notation. However, you could use other system of notations, and then you could get stronger versions. And the one that we're thinking of now is to work with the fast-growing hierarchies up to epsilon naught. That should give us independence from something like ID1, right? But that's all work in progress, and that's yeah, that's all I wanted to say. Thank you.
Okay, thank you very much. Yeah. So what is here? Yeah. Okay. So I guess this interesting part, especially interesting for how it works with this sandwiching. So that's a kind of new thing that doesn't have any analogs, so to say, we can think about. Right?
So strangely enough, this is actually the old thing. So this work with the sandwiching, it's already been published in the Proceedings of the AMS. Mm-hmm. This new work is with the weaker versions. But historically, the way this happened was, actually, Andreas knows this much better, but the way I understand the story is that in discussions with Arai and Weiner, they suspected that the simple version would be enough for ATR naught. The proofs mm-hmm. didn't quite work out. So Andreas came up with a new version, that's right?
Yes.
Mm-hmm. And then the proof worked out, and then Andreas went back to said, well, let's go back to the old versions and see if we can, push them down a bit more and get things to work. And that's where this new analysis comes in with the ACA not prime and plus.
Yeah, interesting. So, of course, we usually think about these Ackermannian functions as just somewhere below, let's say, branches of order primitive recursive functions. But here we have the procedure to build with their help something which goes far beyond. So to say, that's a rather remarkable feature of this construction.
Yeah. Well, but this is already present in so the original Goodstein principle, it's based on the exponential function, and because you have towers of exponentials, they're all elementary, but the termination time is bounded by the fast-growing hierarchy up to epsilon naught. So yeah, you always will get this.
Yeah, sure. Once you have this analogy, so to say, in place, this relationship, okay, that exponentiation is somehow crucial for the level epsilon naught there in the usual Goodstein, and you can think about generalizations and it becomes natural. But a priori, I don't think it's obvious. It's such a
oh no, it's very surprising. But now that you have this in mind, mm-hmm. the way we're thinking of it now is, now let's say that you use the fast-growing hierarchy up to some lambda, and you use that to write down natural numbers. Well, the idea that termination should be bounded by the fast-growing hierarchy up to some lambda prime, typically bigger than lambda.
Yeah.
So then it becomes more systematic, because then you have two fast-growing hierarchies. One of them tells you how fast the numbers are growing, and one of them tells you how fast the termination time is growing. And you get this new ordinal operation that goes from one to the next. Mm-hmm. And then what you're pointing out really becomes very, very transparent.
Yeah. Okay. Okay, now I would like to ask, there are many people thanking you in the chat that you can possibly see for a nice talk.
I can't see it now. I could stop sharing, I guess. I'll stop the sharing.
Yeah. Okay.
I don't, how do I see the, oh, here it is. Oh, okay. So I see from, so you're welcome.
But also many thanks for your talk, but other people, do you have any questions
Anna?
for the speaker? Mm-hmm. So
Well, I have maybe a sort of philosophical question.
Mhm.
Uh, so here you did the stuff with Ackermann function instead of the more standard exponential one. But
Yes.
Ackermann is also a specific function. So
Yes.
it's possible that people could invent something else and try to do basically the same work. Could it be generalized, say, to a sort of class of functions which do these iterations, or it is specific, something specific happening, and each, say, movement to another function is, say, some creative work here?
Right. So there are several. It could be possible that somebody comes up with a slightly different presentation of the Ackermann function or something like this, which gives the same result but in a more natural way, maybe. I mean, I think this is natural, but maybe some people will find some other version more appealing. Um, but it's hard to tell if you slightly change the notation or slightly change the normal forms, you could get very different results. So, for example, the Ackermann function is often based on the successor function instead of the exponential. So a naught is just b plus 1, and then
Mhm.
you start iterating the same way. In this setting, so let me get this straight. In this setting, the proof theoretic strength with the sandwiching version drops, I think, to epsilon naught. Is
Mhm.
this so Andreas should know this. I'm not.
Yes, yes.
This is not something I myself have worked on. Um, so now that we're working on extensions for the Bachmann-Howard ordinal, there's also several candidates for the functions, and sometimes you get something that works more easily. Sometimes you get something that feels more natural. So yeah, there's a lot of uh, flexibility here, and there's a lot
Sensitivity.
of surprises. Again,
Yeah.
sorry.
Well, I said sensitivity to various technical details that you may choose in your definitions, right? How
Yes.
how many times you iterate to
Yes.
define
So
the Ackermann? Yeah, and I suppose there is also
yeah. So you.
dependence on the specific choices of fundamental sequences if you do it, or is it not so that much sensitive?
Well, that's yes, it is, but for the proof. So the principle is going to be it's going to have the strength that it has, right? You can't, but maybe you're trying to prove that it's independent, and it turns out that you can prove it. You cannot prove it with fundamental sequences, let's say based on the theta function, but you can based on the psi function. So so when proving independence, you really do need a system of fundamental sequences that works well for you.
Mhm.
When you're in the good same side, you're just subtracting one. So uh, the fundamental sequence could be read out of the notation, but there it's just what it is. Subtracting one is what it is, and you have less flexibility in that sense. Um, but yeah, the you have to work with the good fundamental sequences. You need the Bachmann property, as I mentioned, for example. So if
Yeah,
you don't have that,
for sure.
it's much harder to prove that this works.
Yeah. Yeah, my understanding, that's my interpretation of Stepan's question was actually whether you can develop some sort of general theory. Suppose you have a system of functions satisfying certain good monotonicity properties, for example. Using this system of functions, you define some sort of normal forms using procedures similar to what you did. And then see how, let's say, the selection of, let's say, the function measuring the length of these Goodstein processes based on the corresponding system of notation depends on the, or compares to the size of the original function. So,
right. Well, yeah, but
attempted generalization along these lines, let's say.
yeah, but the reason for my answer was to state that you will only get so far with such a general result because of the sensitivity. So
Yeah.
you can't expect you know a one-to-one correspondence. Maybe some lower upper bounds, maybe, but I don't expect anything too sharp. You really have to get your hands dirty each time.
Okay. Okay. Good. So, are there any more questions from the audience? I'm glad that many people from various countries attended this talks, 21. So
Wow.
that's quite nice. So
Well, thank you all for joining.
yeah, thank you
I
very
haven't
much.
seen the list of participants. Here it is.
Yeah, in a week we will have a talk by Dexter Cozen on something which I don't know yet what, but we know him as a famous person in let's say various applied aspects of logic. So come again to this seminar. And yeah, thank you very much, everybody. And thank you, David. Yeah.
All right. Thank you again for the invitation.
Mhm.
Bye-bye.
Bye. Bye-bye.